Morning, guys. So over the last 2 days, we started looking at solution chemistry, basically taking solids, dissolving them into mixtures. We're going to assume that we're very far away from what's called the saturation limit. Basically, all liquids have a certain maximum capacity to be able to dissolve a certain amount of material. Towards the end of yesterday's class, we started looking at dilutions as well as mixing questions. Basically, the notion is as you add water to it, the same thing would happen even if I did a boiling and evaporating off all the water. I'm going to assume all the solvent leaves, but it's the moles that stay behind. So our main formula that we derived from there was C1V1 equals C2V2. We just needed to have consistent units, so the same units on the left side, right side. Today in our gas law section here, we're going to see another similar calculation where sometimes we can just set up consistent units so that they actually match up. So we're going to take a pause here from the solution chemistry stuff here. We're going to look back at our gas laws here. I want to readdress a question that we had from earlier. Up to this point, we've had a bubble for volume for gases at STP. We've been using 22.7. I want to verify with you in this lesson here, where do I get that 22.7? And especially address the notion, well, what if we weren't at the standard temperature pressure? What sort of correction terms or correction factors or calculations can I do to actually figure out how to convert between liters and moles? So just a case in point here, do keep practicing drawing this diagram for yourself here. We can go moles to a certain number of particles, right? 1 mole is given by an Avogadro's number. Right? Careful of the molecules and atom distinction we did earlier. We did moles over to a mass, right? That was called molar mass. You just looked at your periodic table for that. We did this next bubble here, volume of gas, assuming it's STP. You can always pretend it's STP unless you're otherwise told. We'll rehash that in today's lesson here. We could say 1 mole of any gas was 22.7 decimeter cube. And then we did for our solution stuff here, another volume bubble. How do I know whether I'm going to go down this leg or the other leg here? It depends on whether we're a solution or gas. If we're a gas, it is always going to be 22.7. If it's a solution, if there's a capital M to it, we're actually going to use concentration to do my conversion factor N over V. So today what I'm interested in is rehashing where did I get this 22.7 from? And again, in case we are not at STP, how do we then do the conversion? How do we get back to this mind map here? So you're going to find this handout here under the resources section. I would just print off a copy of this and you can just scribble over it with me here. In terms of these gas laws here, we're going to look primarily at 3 variables. For gas laws, we're interested in studying the pressure on the gas, how sort of squeezed the gas is. We know pressure is sort of applied by particles actually hitting the walls of the container, so that's given by pressure. Volume is definitely going to be the size of the container. Sometimes we make the container something very rigid, so the size doesn't change, or maybe we use a balloon instead. A balloon has stretchy walls, can actually expand depending on how many particles, how fast those particles are moving. And we also have temperature. In general, temperature is a measure of the average kinetic energy. The hotter something is, it ends up moving quicker. How come we're interested in gases? Well, solids in some sense are a little bit boring. Solids, the particles don't have much kinetic energy. They're already sort of so tightly packed together. They're just vibrating in place. You can't really change their pressure volume all that much unless you have really, really intense pressures and volumes. In the same way, liquids are also incompressible. Liquids, although they have a little bit more energy, they're slipping aside and past each other here. Pretty much the volume that they take up is going to be the volume. You can take a piston and you can squeeze this beaker as hard as you can. Unless you have really, really intense pressures, the pressure is not going to change very much. Not so with gases, and we're going to primarily look at gases this lesson. For gases, we said, based on kinetic molecular theory, the particles already have a lot of kinetic energy. They're already spreading out throughout the container. They're already traveling really quickly and spreading really, really far apart. So let me just label those terms for you here. They sneak in here. I do want to have a fixed mass of gas. So I don't want to sneak in, oh, at one point here the balloon was this size. When you weren't watching, I just pumped in more gas. I'm not doing that. The balloon is sort of tied out. The gas particles in there are just sort of stuck inside. In this case here, the balloon here will be at a certain temperature. The temperature here will set basically how fast my particles go. Even though temperature here is an average, there's always going to be some particles faster, some particles slower. That's actually going to decide how big this balloon here can actually expand to. So that's the temperature. It's going to basically set the volume, set the size of the balloon. Remember, for volume, I'm not interested in the volume of the particle itself. I know the particle made out of elements, right? It has substance, it has matter to it here. I'm not looking at that volume. I'm looking at the volume of the total balloon as we're at this temperature. What we really want to do is we really want to actually say pressure as well, pressure inside this balloon. Although it's a little bit hard to put a pressure meter inside once the balloon is all tied up, what we're going to do is we're going to say, well, wait a second. We know there's an atmospheric pressure out here. There's something that's trying to keep the balloon from expanding over to overall size. If the particles in the balloon are pushing harder, traveling faster than the outside, the balloon's going to expand. If the outer pressure is higher than the inside pressure here, the outside pressure is going to squeeze the balloon, assuming the balloon doesn't break. So therefore, we can very easily, even though we label the pressure on the outside, in fact, the internal pressure has to be matched with the external pressure for the balloon to stay this size here. So even though I'm going to be putting the P on the outside, we know that's equilibrated. We know that's actually same as what's on the inside. So we're going to specifically look at gases. Because they look like this, there's so many gaps and so many spaces in between. These ones here will respond really drastically. If you take a helium balloon and you just walk outside on a cold day, the balloon's going to cool down, right? It's really drastic change because some of those sizes of the balloons are going to change. Before we get into our main gas laws in this section here, I'm going to, just for completeness sake here, introduce to you an Avogadro's law. This will become more important as we do our stoichiometry next week. But basically, Avogadro, same guy who did the Avogadro's constant, he worded his laws here that equal volumes of any gas always contain equal molecules. So he made the generalization here that, again, it didn't matter what gas you are, as long as you can guarantee the temperature and pressure doesn't change, as long as you have this volume, you will always have this molecules. We've actually already been doing this here. So far, let's say I have a balloon. Let's say I have 1 mole's worth in here. And let's say this time it's actually oxygen. 1 mole's worth here, we can assume STP. How big is the balloon? Well, the balloon here is actually 22.7. What if I swapped it out? I think I swapped it out previously for 1 mole of xenon tetrafluoride. The molecule itself is a lot larger. But again, I'm not considering the volume of the particles themselves. I'm interested in, as long as I'm at a certain temperature and pressure, in this case here, I'm assuming STP. There's nothing really special about STP, it's just a nice reference. Assuming what we're at the same temperature and pressure, it didn't matter whether we were oxygen or whether we were the xenon tetrafluoride, our balloon size, 1 mole of it, would also be 22.7 decimeter cube. So that's why it's saying here, as long as you have equal volumes, I can guarantee you have equal number of molecules inside. So again, they write that for you. The 22.7, that's actually on your data table in case you forget. And they even tell you here our standard temperature. Remember, just for chapter 1, standard temperature is 0 degrees, 273. Later on, when we actually get into the gas laws, if they just say STP, you can type in standard temperature yourself. Standard pressure was redefined. It used to be 1 atmosphere. 1 atmosphere here used to be 101 kilopascals. We'll see that on the backside. But now we're going to use our new standard pressure. And again, we had wrote that conversion down. 1 mole of any gas is 22.7. This actually gives us a nice conclusion for next week as well. We don't necessarily have to be STP, but the conclusion here is the temperature can't change over the course of the reaction. So I'm going to take a look at a fairly famous equation here. This equation we're going to see multiple times. It's called the Haber Process. It takes really inexpensive gases that were already in the atmosphere. N2 is about 78-80% of our atmosphere. Hydrogen's in the atmosphere here. And it basically takes these gases and reforms them into NH3. I'm going to emphasize here these are going to be all gases. We'll actually catalyze it with iron in chapter 3. But that there, I'm going to give you the name. This guy here is called the Haber Process in honor of Haber. So what we're going to be doing over the next couple lessons or so as we introduce stoichiometry, we ultimately want to put all this conversion stuff together, grams to moles, moles to liter, moles to number. We ultimately want to be able to answer the question, if I have a certain amount of reactant, if I have a certain amount of ingredients, and I know the recipe of how the ingredients actually mix together, can I actually make predictions with, well, how much product would I expect if I had this much ingredient? What if one of the ingredients runs out? Right? I should be able to make some comparisons based off this recipe. What we're going to see in the upcoming lessons here is we're going to really rely on these coefficients because the recipe gives you a lot. Sure, it's been simplified. It says for every 1 part N2, 3 parts H2, it produces 2 part NH3. I want to figure out when these coefficients work and when these coefficients don't work. So what the recipe says for us here is for every N2 molecule you take, it's going to take 3 H2 molecules, and it's going to create for you 2 NH3 molecules. That's the recipe. What if I go to the store and I buy 10 N2? Can I still use the recipe? Well, of course, the recipe's been simplified. It just gives you the proportions. In this case here, so far if I have 1 molecule of N2, it's going to need 3 times molecules of H2. It's going to produce 2 molecules of NH3. What if I said 10 molecules? Well, 1 to 3 ratio. I would need 30 molecules. I produce 20 molecules. Easy. What if I have 1 mole? 1 mole is way more than a molecule. But again, it just scales up this way, right? So 1 mole is an Avogadro number. Because the ratio is 1 to 3, 1 mole will require 3 moles of H2, and this will end up creating 2 moles of NH3. So far the conclusion is our recipe will work as long as we're comparing numbers of particles to other numbers in the recipe. So molecules to molecules, atoms to atoms, moles to moles. We're going to see this conversion later on be called the mole ratio or the mole bridge, because it gives us a really handy tool to predict, based on this much ingredient, how much reactant I would expect. When does this recipe, although the recipe itself is good, but when does this 1 to 3 to 2 not work as easily? If I said instead, I have 10 grams of N2. This time, although the recipe does say 1 to 3, I can't come along and just say 30 grams and 20 grams. Why not? In this case here, well, we've done the study here on molar mass. Basically, well, these are different elements. Nitrogen weighs 14 times 2, this weighs 28. Hydrogen only weighs 1 times 2 is only 2. Mass means something different. So although numerically, it is a 1 to 3 to 2, that's the proportions that are going to the recipe, we see that mass doesn't work so nicely. In fact, there are many things that don't work nicely. If I had said instead 100 milliliters of this, again, depending on the different densities, the volume here doesn't necessarily follow the ratios. What Avogadro's law actually allows me to do is it says, because temperature and pressure are the same, right? I'm not sneaking in and I'm not saying, oh, you didn't see me, I just heated it up or I increased the pressure, whatever. I'm assuming the temperature and pressure are the same. Doesn't even have to necessarily be STP. If I have an equal volume, it doesn't matter what type of gas it is, it always contains equals molecules. Hey, molecules is a number, then that means for gases, the volumes will follow the mole ratio. So in general, when this recipe 1 to 3 to 2 wouldn't work for grams, wouldn't work for milliliters, it does actually work for gases. 100 mils, if this is any gas, as long as they guarantee me there's no mention temperature and pressure are different, I can actually conclude, well, it's actually 300 mils, even though this is a totally different gas, because I know the gas volume only depends not on the identity, not on are we nitrogen, are we hydrogen, what mass we are, it just depends on temperature and pressure. So if the temperature and pressure are the same, again, doesn't necessarily have to be STP, this one here, I can just make a note here. The volume of gas, I'm going to emphasize it's only gas, don't do this for liquids, don't do this for solids. Volume of gas also follow this mole ratio. Also follow the coefficients in your balancing number. So 100 mils of N2 would need 300 mils of H2, and this would predict 200 mils of NH3. So that just adds one extra nice link, extra conversion. If it is a gas, as long as temperature and pressure are not altered over the course of the reaction, we can do that prediction. And I want to emphasize here, we are not necessarily at STP. I could be at 25 degrees. I can be at 5 bars of pressure. That's fine. As long as we stay at that temperature, stay at that pressure, essentially what we would have done if we were at STP, we would have ended up dividing 22.7 here. We would have ended up multiplying 22.7 to get back to volume. And ultimately, regardless of the gas, those 22.7s would cancel out. That's at STP. And again, there's nothing magical about 22.7. We'll see that more in today's lesson. So that one there is Avogadro's law here. More on that next week when we actually take a look more at mole ratios. Let's look at our main gas laws, however. So we start off with these three fellows, Boyles Law, Charles's Law, and we have Gay-Lussac's Law here. Basically what they're going to do is we have our three variables. We have pressure, we have volume, and we have temperature. What they're going to do is they're going to take turns setting one thing to be constant, and what they're going to do is they're going to actually see the relationship, see the correlation between the other two variables. So let's just read it here for Boyles Law. They say nowadays you don't need to know these names, although it doesn't really hurt. So for Boyles Law, what he's going to keep is the temperature is going to be constant. All his experiments are done keeping the Kelvin the same. He found there's actually an inverse relationship between pressure and volume. Inverse meaning opposite. So basically when you increase the pressure of a gas, the volume drops, and vice versa. If you decrease the pressure, you increase the volume. So this experiment can be done fairly simply here. You take a balloon, assume that you do this quick enough that the room temperature actually doesn't change. All you're going to do is take this balloon, let's say you squeeze this balloon here a little bit harder. You increase the pressure. Again, what's going to happen is the gas molecules in here, they were traveling on average at the same speed, they're at the same temperature, but given that they have less room to actually travel in, they're going to collide more times with the inside of the container until they equilibrate with the outside. So as I increase the pressure, I squeeze it harder, I would expect this balloon here to actually shrink. We can actually put this graphically here. At first, we had a relatively big volume because I had a relatively low pressure. But what I'm doing here is I'm steadily increasing the pressure. I'm squeezing the balloon. And as you squeeze the balloon, what you're going to find here is squeezing the balloon actually causes the volume to actually shrink. So when the volume is tiny, the pressure is very high. So that's an inverse relationship here, even though mathematically it's actually a reciprocal function. We'll actually do this on a lab tomorrow. But basically that's what we have. That's graphically what we've shown. Mathematically, you can then write here, to show this upside down relationship, I can say pressure is proportional to 1 over V. So that because volume is in the denominator and pressure is in the numerator here, for example, I increase pressure, the only way for a fraction to suddenly get bigger is if the volume drops. So if there's sort of division relationship here, I know that they're opposites. They're actually going to treat it as a proportionality constant. So this K here is actually a proportionality constant. This K here is going to depend more so on how much particles actually in there, what is my actual temperature. We'll see that more on the backside. What I want to do is a little bit of manipulation with this formula here. I know pressure is proportional to the 1 over V. Pressure is K times 1 over V. What if I just did a little bit of algebra, I brought the volume up, I would have pressure volume equals constant. At first you would think multiply, oh, they actually help each other. But remember, this proportionality constant has to stay fixed. This number here actually is constant, so this number here actually can't change. So what's going to happen here is, what if I increase the pressure suddenly? For two numbers to multiply to always give you the same number, that means the volume has to drop. So where previously multiply looked like it would be helping each other here, because they both always have to multiply and always have to hit this constant, it's actually an inverse relationship. And in fact, what we typically say, I can have a P1, V1, those are my starting conditions. If you change pressure, maybe now I'm a P2 and a V2, whatever you change it to, if one drops, the other has to go up. They always have to multiply to give K, so therefore P1, V1 has to match to P2, V2. That's a statement of Boyles Law, assuming that we have constant temperature. All right, let's skip ahead 100 years here. Another fellow, Charles's Law. Again, technology was steadily improving here. He decided to do an experiment with keeping another variable constant. So in this case here, unlike Boyle, who kept temperature constant, Charles actually kept pressure constant. This one here is actually a lot more common than we think. In this case here, at constant pressure, well, if I have a balloon and I just stay roughly the same elevation above sea level, I'm always at a constant pressure. This time what I'm doing is I'm not arbitrarily coming in and squeezing a balloon and seeing what happens. I'm just letting the balloon go, and what I'm testing for is I'm actually testing for the relationship between the temperature. Notice it does have to be absolute, you see that in a second here, the temperature and the volume. So let's start off here at a low temperature. Well, we would expect low temperature, particles are moving very sluggishly, the particles don't really collide, really expand into the container, the size of the balloon is very tiny. But as you increase the temperature, the balloon is going to start expanding because the particles start moving faster and faster. So in this case here, volume goes up as well. So we call that a direct relationship. In this case here, a direct relationship, we get both of these graphs here are linear relationships because you see that they're straight lines. For it to actually be this word here proportional, this proportional word here actually means it actually has to go through the origin. There can't be any y-intercept. So when you're thinking y is mx plus b, you have to be proportional, meaning there actually is no y-intercept. Sometimes we purposely leave in a y-intercept to figure out how much systematic error we have, but we're setting it up in such a way to actually get it to always go through the origin. So linear trends are nice. Lines are really easy to fit to. You can just calculate the slope, the gradient, and all that. What he did is he actually took a real gas. Let's say there's methane in the balloon here. Let's say at room temperature, he figured out the size of the balloon. He heated it up, the balloon expanded. Heated it up some more, it expanded. Cooled it down, it cooled down. Cooled it down. Because it is a gas, even when we drop into the negative Celsius, gases are covalently bonded, London forces, they're still going to be gases, no problem. What he found was for methane, he could actually extrapolate this line here there seems to be some special temperature that this would be cold enough. The particles are actually traveling so sluggishly that the balloon actually doesn't have any size. It would actually have a point volume. You basically stolen away all the kinetic energy that the balloon is a point mass. What you did then is you tested another gas with maybe at a different constant pressure. You test another gas here. Maybe that gas here actually had less volume at a temperature. But what he found here was no matter what gas that you tested, it seemed like all of these gases here actually extrapolated, actually went back to this unique temperature. This unique temperature is actually what we're going to now call absolute zero. It's a theoretical value here. We can never get there, although we've gotten really close. I think we've gotten into the millikelvins. We've gotten to 0.001 Kelvin or so, that order. But basically, this would be the temperature, the absolute coldest temperature. It is absolute scale, so that way we only have positive numbers. And therefore, this is the coldest something can get. All gases extrapolate here. What if I now just reset my graph? I don't want these trends to just be linear and have y-intercepts. What if I just reset my actual zero to the actual coldest temperature? So that gives us our first formula here, the absolute coldest temperature here. This second graph here on the right-hand side here is basically rescaled. It's moving the x-axis. The 0 degrees Celsius would actually correspond to now a 273 Kelvin. All we've really done here is we've moved the axis over. So now it actually does run through this theoretical origin. And in that case there, we actually do have a direct proportionality factor. Because we are on an absolute scale, you will want to convert the Kelvin temperature is the Celsius temperature plus 273. If you want to be really precise, you can go 273.15. But it basically is just a resetting of the zero so that we no longer have any y-intercept. We're going to see exactly the same thing here with Gay-Lussac's law. For Gay-Lussac, he tested the last sort of combination. We had these three variables here. We have volume being constant. So this time he made the size of the container here something heavy duty. So this is not a balloon. It doesn't stretch anymore. What he found was the pressure that the gas applies, how hard these particles here are actually colliding with the walls of the container, are actually proportional, again, to this absolute temperature. All just saying you want to make sure you're converting everything over to Kelvin. So what he found was if you increase the temperature, the particles end up moving around faster. Earlier it was the balloon stretches out, but this time it's a very hard container, hard walls. So what's going to happen here is, all that's going to happen is the particles are going to end up colliding. They're going to still have they're going to hit a little bit harder because they're a little bit harder, and they're going to collide more frequently, a little bit more oomph to their push, and therefore the increased temperature actually would increase the pressure as well. Again, a direct correlation. When one goes up, the other goes up. We had rescaled it so that there's no origin. That way we need to have absolute temperature. Let's see what happens to the math there. So we have pressure is proportional to temperature. So we can actually write pressure is proportional. They say K3 because the K could actually be different from the other Ks there. I can actually rearrange that there. So P over T. Just like before, normally when you think of a divide, you think, oh, they're actually going against each other. But again, let's keep in mind, because K here has to be a constant, this division always has to hit some number. If the pressure, let's say, got increased, the temperature would also need to climb as well. If the pressure decreased, the temperature would have to drop. That actually says a direct correlation with this divide. And what they do here is, because we're set up equal to constant, I can do this first, P1, T1. I can compare it to the new situation, P2, P2, T2. Just careful, in this case here, this one here has to be an absolute temperature. We're going to do a lab in tomorrow's lesson here. I'm going to introduce to you how you can use Excel as a spreadsheet just to help with a lot of calculations, a lot of neat tools here. We're going to link it with a simulation where you're actually going to collect some data down to test out Boyles Law, Charles's Law, Gay-Lussac's Law. And you're going to actually use Excel to actually plot these graphs. You'll notice we preference having a directly proportional relationship if we can, that one that goes through the origin. If we backtrack here to Boyles Law here, most of the graphs here did end up being straight lines. It was only Boyles Law that was actually an inverse relationship. That was an opposite relationship. Although a reciprocal function here is not impossible to fit to, in physics more so what we do is we can actually linearize the graph. We can actually play around with what variables we're actually plotting against each other. Sure, if I plot pressure directly against volume, I have like P is equal to K times 1 over V. I have that annoying 1 over V sort of relationship. What if instead, when I do graphically here, what if I plot, sure, pressure is still Y, but what if I plot a new horizontal axis, and the horizontal axis is actually going to be 1 over volume? So that's akin to taking all the volume readings that you're going to get in your simulation, taking the reciprocal of it. I'm actually hiding that division there, and therefore I'm going to just get simply y is equal to kx. I'm going to get, again, a proportional factor. It's not having any y-intercept, and now it actually is a straight line, although we're plotting pressure against 1 over v. In this case here, just the fancy wording of it, we will only need to linearize this graph here. Linearizing is changing the variables so that we end up hiding the ugliness of the curve and ending up having a straight line, and therefore we can more easily fit to it. So more on that in tomorrow's lesson. I told you we didn't really need to know Boyles Law, Charles' Law, Gay-Lussac's Law, because if you flip over the backside, these ones here actually work hand in hand, which really shouldn't surprise you all that much because they're the same variables. They're just playing around with which one do I hold fixed and then which ones do I end up changing. So in this case here, this one, for whatever reason, they don't give you on the formula sheet. So do memorize this gas law. And basically here, basically here, this is a combination of the 3 gas laws from earlier. We call it the combined gas law. And what it does, how do we know to use this gas law, is it relates one set of conditions to another set of conditions. It has this notion of this is the before, and here's now I'm interested, what's the new volume, what's the new temperature afterwards. Whenever there's notable change, we can memorize this expression, the combined gas law P1 V1 over T1 is equal to P2 V2 over T2. For the units of this here, just like our dilution formula, pressure and volume are supposed to be consistent. So as long as the units are the same, they don't necessarily have to be SI. We're just setting up a ratio. For example, if pressure were ugly in atmosphere, this is atmosphere. Maybe volume is in centimeter cube, right? It's ugly unit here. As long as the units are the same, all those other conversion factors would cancel out. The only one that has a strict rule here is because we actually have to be on the absolute scale for this direct proportionality, the temperature has to be in Kelvin. So you can't just be like, oh, temperature Celsius, oh, as long as the other side Celsius is fine. If you look into the math of it a little bit more, the reason is most of your other conversions are multiply and divide. It's just this conversion to Kelvin. I listed it for you here. You'll notice that conversion is actually a plus. So if this one here really were Celsius, if you end up adding 273 converting to Kelvin, there's no guarantee if I minus 273 on the other side, it actually cancels out. Now they might still give you the problem in Celsius. What I would do first is I would let's take their centigrade or Celsius temperature, let's convert to Kelvin. When it's in Kelvin, I can use this formula. My answer would come out in Kelvin. Let's say I was looking for the new temperature. They can still ask me for the final answer in Celsius. Once I know what the number answer is supposed to be in Kelvin, I can then reconvert over to Celsius afterwards. So outside of this formula, you can convert to Celsius, no problem. But as long as you use this one here, it has to be absolute. Pressure and volume are just consistent. Now let's make sure here, where did we get this formula from? Earlier I showed you the derivation for Boyles Law. Again, we ended up with this relationship P1 V1 equals P2 V2. That's when temperature remained constant. So let's see if that's what the combined gas law says. Combined gas law also says P1 V1 equals P2 V2. Let's assume temperature is constant. Let's assume temperature is 273 and 273. Well, if they're the same, they cancel out. There we go. We get Boyles Law back. I derived for you Gay-Lussac's Law. Gay-Lussac said P over T is equal to P over T. So that's why we have this P over T relationship here. Gay-Lussac's Law would be P over T is equal to P over T. What was he keeping constant? He was having a very rigid walled container. He kept the volume constant. If the V's are the same on both sides, they cancel out. We get Gay-Lussac's Law. With the very same derivation, you can try it out for yourself. For Charles' Law, because it's directly related, when you bring the T over, we'll also get V over T equals V over T, and that sort of matches the last set here. Charles' Law, V over T, all at constant pressures when they cancel out. Those are all 3 laws together. So I want to just skip down here on the backside. How do we know whether to use this one or the ideal gas law, which is upcoming? Again, we have to have a notable change in condition. There has to be a before and there has to be an after. So as you read question 1 and 2, I want you to see if you can identify what's the before and what's the after. In this case here, we're interested in a sample of oxygen gas. This gas here happens to be at 1 bar. Bar is the unit for pressure. Let's call that P. The 295 Kelvin, we know that to be a temperature. It occupies, the balloon spreads out into a container that's 364 milliliters. Now what they're asking you for is almost like what new volume? What's the actual volume if we actually change up our conditions, if the new temperature is now 373 as opposed to the 295, and now it's 255 instead of the 1 bar that we had earlier. So you see that there's actually a notable change. I'm just going to label these ones here, V2, T2, P2. and this one is P1, T1, or V1. Whenever you have this, whenever you have a comparison of before and after, you're going to go straight to the ideal gas law. When you do the ideal gas law, you want to just keep in mind P1 V1 over T1 is equal to P2 V2 over T2. Remember the top units, they just have to have consistent units. They just have to be the same unit. On the bottom here, we actually have to always be in Kelvin. So if I just want to match up the units here, for a pressure unit, oh, not so nice. P1 is bars, P2 is actually kilopascals. Let's just look up our conversion here. 1 bar is actually equivalent to 100 kilopascals. Let's instead write 1 bar. Let's write that as 100 kilopascals, and at least the kilopascals then match up. How about for volume? The V1 started off with 364. That was the initial size of the balloon. I want to know my new volume. Well, if this time volume is going to be milliliters, as long as my final answer I know it's going to come in milliliters, that's fine. For the Kelvin temperature here, they actually gave you the absolute scale. You're going to find that the formulas in this section here are not all that bad. The hard part is just actually converting the units. So let's just write it down here. I'm going to plug in my P1. So this is going to be 100. I'm just going to show you the units, so how I'm matching it up. I'm going to multiply it by 364. That was the volume initially, divided by the Kelvin temperature at the beginning, so 295 Kelvin. Let's match that up with our P2. Our new pressure is now 255 kilopascals. You notice the kilopascals match up. I don't know what the V2 is, but I know I'm expecting it to come out as milliliters, and I'm going to divide it by the new temperature, which is 373. You can do a mental check for yourself here. As you increase the temperature, you expect the volume to expand. However, I'm also increasing pressure. I'm also squeezing the balloon. It's going to actually contract. This time I want to know, well, which one actually wins out. Again, the math is quite simple. 100 times 364, divide 295. I'm going to multiply the 373 up and then divide 255. And I get an overall V2. Double check my numbers. I'm getting 180. Well, what unit would it be? We had said units are going to be consistent, so 180 milliliters. Let's see if we can practice number 2 in exactly the same way. Oh, it's carbon dioxide. Who cares, right? The volume temperature only depends on what temperature and pressure that we're at. This time here, we have a V1, we have a 2 liters, and we're told we're at SDP. So this is why it's important for you to know what is standard temperature, what is standard pressure. Standard temperature, remember in this chapter, was 0 degrees, 273 Kelvin. Standard pressure is actually 1 bar, which is 100 kilopascals. So that's actually the start. They actually sort of shortcutted that. And then what they're asking for here is what's the new volume again? They didn't have to ask you volume. They could ask you what's the new temperature and whatever. But they give you 2 other units here. Again, the hard part about this is just converting your units. Let's say 20 plus 273. What would the Kelvin equivalent be? So this one here is 293 Kelvin. So 273 to 293. This one here was in kilopascals here. What I want to do is I want to convert atmosphere again as a pressure unit. Atmosphere, by definition, atmosphere is 101.325 kilopascals. Let's do P2 here. If I have 0.860 atmospheres, I multiply it, we have 101.325 kilopascals. Sometimes they just do 101.3. That's going to be, 1 atmosphere. Sorry, my bad. 1 atmosphere is 101.325 kilopascals. That way, when you check your units, you see that they always cancel out. 0.86 of that, 101.325, gives you 87.1, give or take. If you can keep the whole number in your calculator, all the better. Now that the pressure unit is the same, you can then punch it in the same and actually calculate the new volume. So careful, you do actually know what STP is. Sometimes you just shortcut that. As you start looking at question number 3, question 4, you're going to see it looks very similar. We're still given some of very similar information. We're interested in finding temperature. They actually throw in a moles now. But likewise, they actually give you a volume and a pressure. Later on, we have a pressure, a volume, a temperature. It's very familiar. However, what I want you to compare is there is no before, there's no after. There's no, here's what it was before, and now having changed temperature and pressure, what's the new volume? This time here, they're just saying, here's my balloon. That's my pressure. This is P. This is my, this one here is volume, decimeter cube. My pressure is going to be atmosphere. I happen to have N for moles. This is my volume, this is my pressure, this is my moles. What's my temperature right now? So I'm not changing anything here. Same thing in question 4. I have this pressure, I have this volume here, I have this temperature here. I'm not, when I heat it up or when I squeeze the container. It's just one setting. And in that case there, instead of using the combined gas law that we practice here on 1 and 2, we're actually going to use what's called the ideal gas law. We're going to derive a law for a perfect gas. We'll come back and talk about what makes it ideal. This formula here is in your data booklet. You just need to know to use it. It's PV is nRT. Where they actually got this, if you take your P1 V1 over T1, so far the combined gas law from the Boyles Law, Gay-Lussac, and whatnot, these ones here all had to equal a constant. All I'm doing here is I'm actually qualifying for you what this constant is. In fact, this constant is actually made out of at least two parts. It's made out of N. This is actually the moles of particle. We said we just want to keep it constant in the balloon. I don't want to suddenly add more particle or take away particles when you're not looking, but that's going to be the N. And I can actually multiply it by what's called a universal gas constant. That universal gas constant will always be 8.31. If you look at another textbook here, it may be a different set of units, a different number, but we're going to use the SI one here. That actually is a universal gas constant. Regardless of what gas I'm looking at, regardless of where I am in the universe, that's always going to be R. So because of that, I'm just going to take this first part. PV over T is supposed to be N times R. I don't like this divide by T. I'm just going to bring the T up, and therefore I end up with the product of P times V. Now I don't have situation 1, situation 2 anymore. I'm just going to drop the subscript. So I'm just going to say P times V has to equal to nRT. Or if you just rearrange that, then it's going to be pivnert. PV is equal to nRT. So this time there is no 1s and 2. There is no before and after, just like you're reading through the question in 3 and 4. Again, the formula, if anything, it's even easier than the one before. Where you're going to have trouble is actually putting things in the right units. Unfortunately, because we don't have a comparison between 1s and 2s, we don't just want to keep the units consistent. We want to put everything technically back in SI units. Technically, all our scientific formulas will only work when the units cancel out properly in their standard units. So what I've done for you here, you probably are wondering as well, how much of this do I need to memorize or whatever. A lot of these conversions aren't given to you, so I would memorize these conversions. So I've given you the constants here. Pressure, the SI unit should actually be Pascal. Up to this point, we've been using bar, we've been using atmosphere, kilopascal. Actually, Pascal is actually the SI unit. So what's the conversion? 1 bar is 100 kilopascals, kilo is 1,000, so 1 bar is 100,000 pascals. And atmosphere, which is a little bit over 101 kilopascals here, we can actually write it 101,325 pascals. So that's how you convert over pascals. Volume is annoying. Volume actually says, well, meters are standard unit. Let's picture a cube that's a meter on every side. What we're going to actually see is a meter cube is actually equivalent to 1 kiloliter. It's just IB doesn't like using liters at all, so it's going to use meter cube instead. I'm just going to demonstrate to you here everything's off by 1,000. So we know decimeter cube was equivalent to a liter. If you want to get to meter cube, which is kiloliter, I would need to divide by 1,000. So that's why 1 kiloliter is actually 1,000 liters. If you want to get over to centimeter cube is equivalent to a milliliter. I need to multiply yet another factor of 1,000, and therefore everything's off by 1,000. That's going to save you a little bit of time, so you don't need to go like, oh, I have decimeter cube, oh, I need to divide by decimeter and get to centimeter, but I need to do that 3 times. It just saves you a little bit of time. It's always going to be 1 step up on the prefix table, but I always need to do that conversion 3 times. How it's shown on the data booklet, it's not all, I need to memorize all this here. On the data booklet, this is what we're given, just for reference sake here. So more to the point here with this volume unit, I just emphasized to you that they're 1,000 off from each other. They actually start off in the data booklet and they remind you 1 decimeter cube is actually a liter. They say I have 1 of this middle one. So if I have 1 of this middle one, I multiply 1,000 to get to centimeter cube. So that's why I have 1,000 centimeter cube, 1,000 milliliters. If I'm this middle one and I only have 1, I would actually need to divide by 1,000 to actually get to meter cube. So that's why I have 0.001. Everything's off by 1,000, and that's how it's worded. They actually gave you the standard conditions here, so you don't need to memorize that. And they even give you the 22.7. That's where we had gotten 1 mole is 22.7. I'll derive that for you in a second here. All right. So volume is an annoying one here, Pascal meter cube. Temperature, we said it has to be absolute. We already saw that conversion. We're going to use moles. We could actually see the entrance again of molar mass, which is gram per mole. Either you look at the molar mass on the periodic table. For example, question number 4 is asking you, well, what is the nitrogen sample? You would use the ideal gas law formula. Maybe I can do this for you here. What I would do is I would just make sure all the units are correct before you begin. So pressure, they give me to me as 501 kilopascals. Well, I actually want pascals. So 1 kilopascal, you can either do that in your head here, is going to be 1,000 pascals. So 511,000 pascals. Volume here, it's liters. So 25.0 liters. Remember, liter was that middle one. I want to get to milliliter. I want to get to kiloliters. So for 1,000 liters, this actually gives you 1 kiloliter, or 1 meter cube. That's the 0.0250. That's actually the meter cube that I wanted. So kiloliter equivalent. So meter cube. Temperature here, again, they gave me the centigrade temperature here, 27 degrees. I want to add the 273. You can do the 0.15 if you like. 27 plus 273 gives me straight 300 Kelvin here. Again, because we're not setting up a ratio, it's taking a little bit of work. Put everything back into the SI units. Put everything back into the correct units before you actually punch it in. And now what we're ready to do is we can actually try to use this pivot formula. PV is equal to nRT. I have PV and T. That means I'm going to be looking for N. How many moles of particles do I have? And given that this is nitrogen gas, this is N2, the molar mass is 28.02 grams per mole. If I know the moles, I can just multiply the 28.02. So let me just rearrange this for you here. The N is equal to PV over RT. I did the hard part already, just making sure the units are correct. So this one here is going to be 511,000 pascals. I multiply it by R. R is a universal gas constant, 3.81 joule per Kelvin mole. Divided by R, which, R was supposed to go down here, 8.31 joule per Kelvin mole. Volume was supposed to go up here, 0.0250 meter cube. On the bottom, I want 300 Kelvin. We're going to show you the units canceling out, but just let me type it all in first. So I have 511,000 times 0.025, divide 8.31, divide 300. And this is giving me an N value of moles of 5.12. I want to just show you the units canceling. So Kelvin cancels this Kelvin here. We are going to pick up a mole down here, so joule per Kelvin moles. So that's where we actually get moles up here. I want to demonstrate for you that a Pascal meter cube on top, so Pascal times meter cube is a unit on top, has to cancel out the joule because we're just left with moles on the bottom. So I want to show you that a Pascal meter cube is equivalent to a joule. Pascal is a standard unit for pressure. If you think pressure here is a force over an area, so if pascals is for pressure, a force is given by a Newton, area is given by a meter squared. For Pascal, I can actually write that part as a Newton per meter squared times meters cubed. For the joule part, joule is a measure of energy. Let's use work as force times distance. Work is a measure of energy as well. Work can be measured in joules. That one there is also going to be a Newton times a meter. I can plug in Newton over meter down here, and you just see that everything else dies away. A meter squared cancels two of them, so meter, and then you see a Newton meter will cancel Newton meter. So that leaves you with just the moles, or long story short, if you put everything in SI units, everything will cancel out. That's the number of moles, and now I'm ready to just convert over to mass. How do you find the mass if I know the moles? 5.12 moles divided by 1 mole. Molar mass here is 28.02 grams. Times it by 28.02, and this gives you the grams. Again, we're using ideal gas law because we're not comparing condition 1 and condition 2. It's just directly using the ideal gas law formula. I guess based on my physics background here, I'm very comfortable using the SI unit. Sometimes in chemistry, people don't like going straight to the Pascal, straight to the meter cube. There is a shortcut that you can test it out for yourself. That 1 Pascal meter cube, this combination is actually the same as 1 kilopascal decimeter cube. Let's figure out why that is. If I had the full SI unit here, pascals, if you wanted to go to kilopascals, you would have ended up dividing by 1,000. If you want to go from meter cube, which is kiloliter, over to liter, which is decimeter cube, I would have multiplied the 1,000. You see that those two terms actually cancel out. So if you like, and you don't want to go fully into the SI units like proper, if ever your pressure is given as kilopascals, as long as you match it up with the liter, the units will also cancel out, just like the SI units would cancel out. Let me end off with one last comment here, since it's on the page. You can try out question number 3 as well. We call this one here the ideal gas law. We say this is a gas in a perfect world. What is it that makes it so ideal? In the IB exam here, they can give you what I call the nature of science question. Basically, it's questions like this. We know how to do the math. We know how to do the calculations. But what are some assumptions that went into actually using this formula? The 2 assumptions that we're making for an ideal gas law is the fact the volume of gas is actually negligible. So let's picture a real gas. A real gas may have size and shape. our ideal gas, we're going to pretend to squeeze all that volume into a point mass. That way we can ignore sort of size and shape. We don't need to worry about these molecules interlocking and twisting and getting tied together. This way they'll just do a very simple bounce off each other. In fact, we're going to link it with another assumption here, no attractive forces. These are the two assumptions that we're making. This one here seems like a crazy assumption. There's always going to be attraction, isn't that true? In this case, your elements will always have protons with plus. There's going to be a bunch of electrons. We're going to see more so in chapter 3. There's going to be a Coulomb attraction. Basically, positive always likes negative, and negative always likes positive. In some sense, they always know each other are present because they're made out of all these charges, and opposite charges attract. And yet what we're saying for ideal gas law, we're saying, yeah, pretend those are not there. Pretend those are. It's as if these point particles here actually don't know each other are present. Seems like a really bad assumption. But fortunately for us here, the ideal gas law actually is a first good iteration. What we want to do is we're always testing real gases. We want to figure out how can I make my real gas look like my ideal situation so that I can use the formula PV as an RT. Because if I'm not under ideal situations, there's going to be a few other correction terms I need to toss in. So they qualify here, a real gas deviates from ideal behavior when they're a combination of low temperature, high pressure. I can summarize that with having very small separation. If your container is very tiny, when your container is very tiny, let me make the container here square, the molecules are going to be really close together. That means these attractions that are always present, the attractions we're going to see get stronger because they're closer, and especially as they have size and shape, they're going to get interlocked and twisted together really, really easily. When will we have small separation? If I cool down the box or if I squeeze the balloon. In contrast, what I want is I want to have big separation. If I want to spread things really, really far apart, sure, I might actually be a real gas, but if my container was actually this humongous, even though I might have size and shape, because the container itself is a lot bigger, the chances of these colliding together is not as high. The chances of them getting twisted together is not as high. Even though there are background attractions between positives and negatives, we're going to find that the farther away things are, it's actually the weaker the attraction is going to be. It's as if they really don't know each other present. So we can actually mimic ideal circumstances. The bigger the separation, what do I need to do to temperature and pressure to make it highly separated? I actually want high temperature, low pressure. I very commonly get people saying, oh, I want STP. Remember, STP was convenient for me to get 22.7, but in this case here, I actually want even more spread than STP. I want the bigger the temperature, the better, the lower the pressure, the better. That way the balloon can expand really, really wildly. That means the particles can be as far spread apart. That's when my real gas actually behaves ideally. All right? So practice questions on your worksheet here. We'll pick it up from there tomorrow. Thanks, guys.